Welcome everyone to day 3 of 5 of Are You Ready for AP Calculus? This is our third day covering all the topics and concepts that I have seen students struggling with before they enter an AP Calculus classroom. So I'm here this summer to help you get through all of that so when school starts for you, you are ready and prepared for AP Calculus. I hope you've been enjoying this series. We've had 2 days already in the past. You can check that out on my channel. Make sure to subscribe, leave a like, and comment on those videos. Let's take a look at day 3. Here we go. First topic for today is end behavior. The key question today is, as x approaches some value, what value is y approaching? Y can also be called a function of x, and that's where we get that f of x notation from. Y is a function of x because whatever x we input, y is what we get as our output, and f is the function that x goes through in order to get our output of y. That's what we call it, f of x. Now that said, let's check out some of these functions. This function f of x equals 1 over x. Let's take a look at what this might look like on an xy coordinate plane. 1 over x looks something like this. It's a rational function, we call it. And as x approaches infinity, meaning as x goes all the way to the right, what y value are we approaching? As x approaches infinity, as x goes all the way to the right, my y values are decreasing towards 0. So f of x here is headed towards 0. How about as x approaches negative infinity? As x approaches negative infinity, goes all the way to the left on the x-axis, f of x again is approaching 0. Okay. Well, everywhere else on this curve, they'll just have actual values. But at x equals 0, we notice something special that happens. As x approaches 0 from the right side, so we use this little positive symbol here, kind of looks like an exponent. As x approaches 0 from the positive direction, my y values are headed upwards towards infinity. Ooh, okay. And as x approaches 0 from the left side meaning from the negative direction, my y values approach negative infinity. So this is kind of what end behavior gets us to. It's the idea of a limit, which we'll talk about at the end of today's lesson and is one of the first things you will be learning in AP Calculus. Let's check out another function, 1 over x squared. We know what 1 over x looks like, so we know that 1 over x squared will just mean everything is now positive, right? This portion in the third quadrant will now be flipped upwards into the second quadrant. Everything stays the same, right? This, the same. This one, the same. This one also the same. This is the only one that really changes. As x approaches 0 from the left, now f of x is also approaching infinity, just like when x is approaching 0 from the right. And this becomes something that we can make use of later in calculus. Let's check out this polynomial. We know polynomial end behavior from pre-calculus, algebra 2. You've seen this so many times. If we have a negative leading coefficient with an odd degreed polynomial, we know that this polynomial will start at the top and end towards the bottom, a little John Travolta action. So as x approaches negative infinity, my y value is approaching, boom, all the way upwards to positive infinity. As x approaches positive infinity, f of x is approaching negative infinity. And this is what we call end behavior, and we're so familiar with this already. Just taking it up to the next level. 2, piecewise functions. Wow, students really struggle with piecewise functions when they get to AP Calculus because we just don't see enough of it in Algebra 2 and Pre-Calculus. If you took AP Pre-Calculus, you should be familiar with these, but if you haven't, here it is today. What does it mean for a function to be continuous at a point? Well, a function to be continuous at a point, let's say we have some curve that looks like this, and we're asked, is this function continuous at this point? Well, that means from the right and from the left, they meet at that point, and that point exists as well. So if we want to find the missing value of a variable that makes f of x continuous at x equals 5, if you notice, this function f of x is split into 2 separate equations, split at x equals 5. So if I plug in 5 into the x and I get the same value for these two equations, then that's what k needs to be. So I plug in 5 into this top equation. That gives me 5 squared. I plug in 5 into the x in the second equation. That gives me 5 plus k. Now we solve this out. 5 squared is 25, so if we subtract 5 from both sides, I get k is equal to 20, and if k is 20, that's where f of x will be made continuous at the x value of 5. We know that x squared and x plus k by themselves are already continuous because they are polynomial and or quadratic and linear functions, and they are continuous on across a domain of all real numbers. But because we have k equals 20 as this unique solution where the entire function f of x will be continuous at x equals 5. Let's try another one of these. So for this one, we're not split up anywhere. We're just told that x cannot equal 2, where the function equation is this top equation. And you can tell why. When we plug in 2 into this equation, this top equation, we get 2 squared minus 2 minus 2 all over 2 minus 2. That'll give me 0 over 0, and we will call this indeterminate, unable to be determined. Not undefined, but indeterminate. What do we do with this information? Well, we can factor this top portion. That factors into x minus 2 times x plus 1 all over x minus 2. Now, in reality, we can't just cross this out, but because we're told that x cannot equal 2, we're given that domain restriction. When we do cancel this out and then plug in an x equals 2, we get 2 plus 1, because all that'll be left is that x plus 1, and that's 3. So what does my function need to equal when x is equal to 2? Great question, 3. Therefore, k must equal 3. And this is how we will be utilizing piecewise functions in order to prove continuity in AP Calculus. And this is kind of like the rough idea that we need to understand before we see these more with limit notation and things like that in AP Calculus. Super exciting stuff. Once again, I've been saying this in day 1 and day 2. If you do not know how to derive all components of the unit circle, check out my day 1 video. In day 2, I said, this is just something you need to know cold. So I'm putting it here again, day 3, when I do these lessons with my students live in the classroom. I used to have them speed draw all the units, all the components of a unit circle. I said, if you can beat me, come up to the board, draw all the components of the unit circle faster than me, I'll give you an A for the semester. No student has ever beaten me in that. I will not disclose the time that it takes for me to do it, because then the students will just try to beat that time before they challenge me. So I'll challenge you as well. Try that out. Let me know in the comments, how fast can you draw all these components of the unit circle, and I'll let you know if you can beat me or not. Number 4 today is rate of growth. Which function grows faster? Which equation, which expression grows faster as x gets bigger? As x gets bigger and bigger and bigger, which of these pairs of expressions grow faster? So 2x and x, clearly, 2x grows faster, but not by much, right? Not by much. 99x squared and 4x cubed. This one might make you think a little bit, but as x gets bigger and bigger and bigger, there's no question 4x cubed will start growing faster, because the 4 and 99 almost become ignorable as x gets really, really, really big. E to the x and x cubed. Now, when we get to power functions as opposed to exponential functions, we will start to see some confusion. And I will tell you right off the bat, as x gets bigger and bigger and bigger, the power function will always grow faster than any polynomial function. Or let's call this the exponential function and this a polynomial function. So exponential functions always grow faster than polynomial functions. And this is only when x is getting bigger in the positive direction. So therefore, here is the power or exponential function will always grow faster than the polynomial function. Let's think about trig functions, sine of x and cosine of x. What is the highest possible value for sine and cosine? When you plug it into a calculator, when you look at the graph, kind of looks like this. We call it a periodic function, and it oscillates between 1 and -1. So the highest it can go is 1. Therefore, x cubed grows faster as x gets bigger. Same idea here. 3 to the x will grow way, way faster than cosine of x. Now let's look at some actual expressions, multi-term expressions. 3x cubed minus 1 and 3 plus 2x. If we really think about this, as x gets bigger and bigger and bigger, do you accept that this negative 1 and this 3 don't really matter in the long run? Like, what's a million minus 1? 999,999. Did that really make a difference to that million? No, right? And as the numbers get even bigger, this negative 1 and 3 won't even matter. So we are only dealing with the superiorly growing expressions here, the terms. So 3x cubed and 2x, there's no question, 3x cubed grows faster. Now let's look at these. E to the x definitely grows faster than cosine of x, so we don't even care about what cosine of x gives us. Same idea here, sine of x grows way slower. It doesn't even grow actually, it stops at 1, right? That's the highest it goes. X to the 98th and e to the x will surely grow faster as x gets bigger. Now we get to something like this. 8x squared grows faster than 3x. 2x squared grows faster than 1. This is kind of similar to what we dealt with up here. 8x squared does grow faster than 2x squared. But when we take x to infinity, this is where we kind of have to pay more close attention. And I'm kind of preparing you for AP Calculus, but I'm going to leave it to your teacher, or maybe I could be your teacher as well this year. If you check out my summer math courses, should be a link in the bio. This gets really cool, and I don't want to steal your teacher's thunder here. So I'm going to leave that as is, or maybe we'll take a look at it right now. Introduction to limits to infinity. Which grows faster, top or bottom? As x approaches infinity, does x to the 5th grow faster or x cubed? Well, x to the 5th grows faster. Now, what do you know about fractions where the numerator is growing faster than the denominator? Let's take a look. Let's start with 10 over 1, and then 100 over 2, and then 1,000 over 3, 10,000 over 4, 100,000 over 5. Where are these numbers going? Well, this is 10 to 50 to 333.3, repeating. 2,500, 20,000. Where are these numbers headed? We're getting bigger and bigger and bigger. And as x approaches infinity, as the x gets bigger and bigger and bigger, we know that this is going to infinity. Otherwise, also known as does not exist, because infinity doesn't actually exist. It's not an actual number. But saying that this equals infinity tells us more information than what DNE tells us. Let's flip it then. What if the bottom is growing faster than the top? A lot of my students would say here, negative infinity. But let's think about it a little more. If we have 1 over 10, then 2 over 100, 3 over 1,000, and 4 over 10,000. Where are these numbers going? Well, this is 0.1, 0.02, 0.003, 0.004, and so on and so forth. Where are these numbers headed? They're getting smaller and smaller and smaller, but never in the negative direction. We stop when we get to 0, right? They're getting smaller and smaller and smaller, and they're headed towards 0. And you should kind of recognize this here, because if we did cancel out x cubed and x to the 5th, doesn't that remind you of our very first topic from today, end behavior? We said 1 over x squared. That graph looked like this. And as x approaches infinity, as x gets bigger and bigger, what did we say this function approaches for the y values? They approach 0. So we're kind of connecting everything here. Topics 1, 3, 1, 4, and 5 today. Let's check this one out. 2 is a constant horizontal line. It's a constant function. 3x cubed minus 1 is growing. So again, the bottom is growing faster than the top. Therefore, as x approaches infinity, boom, that's it. It's really that simple. Now, we just worked with this for our topic 4. We don't even care that cosine and sine are there. Why? Because e to the x and x to the 98th grow faster than their other terms within the numerator and denominator. Since the top is growing faster than the bottom, boom, infinity. Or we can call this does not exist as well. Now let's check this one out. This is where the fun begins. We don't care about 1 because 2x squared grows faster than 1. We don't care about 3x because 8x squared grows faster than 3x. Now, x squared and x squared, they're growing at similar rates. The only difference are their coefficients. So guess what we do? The answer will be the fraction of those coefficients. And that's it. If you learned something new today, or if this was very good revision or review for you, make sure to subscribe. I have days 4 and 5 coming up in the next couple of weeks as well. So you'll be able to access them and get notified for them. If you enjoyed this lesson and you think you deserve it, or you think I deserve it, or this video deserves it, leave it a like. Also, leave a comment. I read every single one and I'll reply to all of you as well. If you ever want to see anything new, let me know as well. I'm going to be doing a lot more AP Calculus stuff in the future on my channel. I hope you enjoy. Check out my shorts as well, and I'll see you in day 4.